Hi, I received quite a lot of queries regarding the practice question that I sent, and from the queries that I received, I think there is a common maybe misunderstanding or lack of understanding of how the clock actually plays a significant part in a sequential circuit design. Okay, I think most of you are still thinking in the combinational logic uh, sort of direction, whereas in sequential circuits we have to remember we have a clock. Okay, so let me just go through the question and how we derive at the answer that I gave you. Okay, so basically in this question we're trying to detect a sequence of ones. Okay, and if you see here the y is the input, z is the output. Okay, so in this situation, okay, when I detect three ones, okay, it is the output is a 1 here. Okay, and over here this is also valid because I still have three consecutive ones, so the output is still a 1. Okay, the moment I hit a 0, I get an output of 0. Okay, and then whenever it goes 1, I need to have three consecutive ones before the output can be a 1 again, like shown here. Okay, so I think that part everybody is clear. Okay, and the state transition diagram, okay, what I've shown you is one with 4 states, and some of you have come up with your a different approach with 3 states, which is also possible. Okay, I will not go through all the possible combination, but as long as you understand the thinking process, I think that is what is important. Okay, so as we have seen, okay, we start off with state 0. Okay, and in state 0, okay, if my input is a 0, okay, I will stay in 0. Okay, I will stay in 0, and my output is a 0. Okay, but my input is a 1, like for example over here, then I can transition to another state called state 1. So at this point of time, what we have is the input is a 1, but the output is still a 0. Okay, and when I'm in state 1, what can happen? If I have an input of a 0, I will go back. Correct? If my input is a 0, okay, then my output is 0 and I go back to state 0. If my input is a 1, I can transition to state 2. Okay, at this point of time, my input is a 1, but my output is still 0. Okay, so if you see down here, this is the first one, this is the first one, and this is the second one. Okay, and now I want to detect the third one. So when the third one comes in, I can go to another state, state 3. Okay, so this is the third one, and at this point of time my output will be a 1. Okay, so this is important to remember that this is the third one. Okay, so I've detected 3 ones in a row, and now this is the output. Correct, the output is a 1. Okay, so when I reach state 3, that is where I generate the output 1 here. Okay, now from state 3, if I still have an input of 1, okay, if I still have an input of 1, then the consecutive 3 ones still carries on, so the output is still a 1. Okay, but if I have a 0, then my output will be a 0. Okay, so input 0, output 0. Same thing here from state 2. If my input was a 0, my output would have been a 0. Okay, so this is basically how we can derive the state transition diagram. Again, this with 4 states. If you use 3 states, is also possible. Okay, but then you have a don't care state. Okay, which you need to be which you need to probably check to see if eventually after you do your reduction, does it come back to a self-correcting circuit, okay, as you saw in your tutorial. Okay, so in this case, since we know we need 2 bits, we can use all the 4 states, okay, and solve the question very easily. Okay, if not, if you use 3 states, also possible, but just be careful of the don't care conditions. It will be good to check if the don't care conditions, after you do a simplification and you have the assigned ones and zeros, does it go back to the idea of a self-correcting circuit, as you saw in the tutorial questions. Okay, now quite a lot of you have a common question, which is this case here, where, for example, here in state 2, one question is in state 2, my input here is a 1. correct? Okay, my input here is a 1. So at this point of time, I already have 3 ones. Correct, I already have 3 ones. Then why is it that my output here is still 0? Correct, that is one common question. And another common question that I have been receiving is, in this case here, where my input in state 3, when my input is a 0, why is my output still a 1? Okay, so these questions, okay, basically relate back to what I said in the beginning just now, the idea of clocking. Okay, the idea of clocking. If you look back, okay, so if I go down just to look at the sample solutions that I've given you, if you look at the circuit here, okay, if you look at the circuits here, y, okay, y is eventually propagated through some circuits or directly, whichever circuit design you have, and presented as the input to the flip-flops, okay, whichever design that you have chosen, either the D flip-flop or the JK flip-flops, okay. So what does that mean? Okay, what does that mean? It means that, okay, it means that when y changes, the circuit does not immediately process the new y. Okay, always remember this. When y changes, the circuit does not automatically process the new y. It has to wait for the clock cycle. Correct? It has to wait for the clock cycle. Okay, so let me draw out a scenario here. Okay, hopefully that gives you a better idea of how it works. Okay, so let's look at how things will be. Let's look at the clock, okay, and the y and the z. Okay, so I'm going to draw some clock signs here. Okay, so I'm going to draw four clock cycles. Okay, and I'm going to make it such that it's a positive edge triggered design. Okay, so now let's think of the scenario where I'm going to have 3 consecutive ones. Okay, 3 consecutive ones. Okay, so when I have 3 consecutive ones, okay, so for the inputs, okay, the inputs, okay, of course, in theory we sort of may draw the signals changing together with the clock, but in practice, in reality, the signal must always be ahead of the clock. That means the signal must be prepared and must be ready before the clock comes in. That means if I'm going to process, okay, at the clock edges, okay, so these are the clock edges. If I'm going to process a signal at the clock edge, the signal must already be available before the clock edge comes in. That means somewhere before the clock edge comes in, I must already have the signal ready. Okay, so in this case, y is going to be a 1. Okay, so when y is going to be a 1, okay, so what am I doing here? So if I look at the output here, the output z is generated when, okay, so z is the output of the circuit, and the output of the circuit means the circuit must process the input through the gates and the flip-flops and then generate the output. Okay, so if I just go back to the circuit here, you can see that the z here is the output. Correct, z here is the output. That means z does not immediately change the moment the clock comes in. It has to process through all these circuits that you have here. Okay, so it takes a bit of time for the z output to change. So after some time, the z output will change. Okay, so how much time depends on, of course, the actual circuit that you're building. Okay, so let's put a time here where the output z is expected to change, okay, after the clock comes in. Okay, so at this point of time, this is before I came in, I was in state 0. Alright, before I came in, I was in state 0. Okay, so assuming that earlier it was 0 and the output was 0, and the first clock comes in, I go to state 1. Correct, I go to state 1. Okay, now, so I carry on with the input here, okay, and y remains. So at this point of time, z will also remain. Okay, now since y is going to carry on being 1, at the next clock cycle, what will happen? I will transition to state 2. Correct? Okay, so what we must understand is the ones that we are monitoring. So this state 1 is the first one. So this is the first one, correct? And this is the second one. Okay, and my y is still carrying on. Y is still carrying on, and my z is still 0. Correct? My z is still 0. Okay, and since my y is carrying on, at this point of time, what happens? Okay, at this point of time, what happens is I have registered. Okay, I have registered my third. Okay, third one. Okay, so when I register my third one, I also transition to state 3. Correct? I also transition to state 3. So when I transition to state 3 is where the output will change. Correct? So the output will change a bit of time after the clock changes. Correct? Okay, so it will carry on to be 1. So if you see down here, basically what is happening is, okay, maybe I should draw this correctly. The first one is so the first one is registered upon this first clock here. Okay, it's at the clock here. Okay, so at each clock, the first or the new input is registered. So at this first clock, okay, when the first one is registered, I transition from state 0 to state 1. In the second clock, I transition from state 1 to state 2. And in the third clock, I transition from state 2 to state 3. Okay, so now what does this tell us? What does this tell us? It tells us that, okay, to address this question here, this first question here, this one here, I'm in state 2 and my input is a 1. Okay, why is my output still 0? Because I need to wait for this clock. Okay, I need to wait for this clock over here, okay, to register the change in the 1. Okay, so the 1 here, this one that changed, okay, could have changed anytime. Okay, even theoretically speaking, okay, or even practically speaking, basically this can also have a transition here and still would not have made a difference. Okay, even if y had changed to 0 in between the clock cycles and changed back to 1 again, it technically does not make a difference because the circuit only samples the y input at the clock trigger point. Okay, so that is how a sequential circuit works. Okay, so let's just go back to how we had it. Okay, so y is 1 all the while. So even though this 1 here, okay, happens, okay, anytime between the second clock and the third clock, okay, we must still wait for the third clock in order for us to register this third input and then transition to a new state or generate a new output. Okay, so that is why we need to wait for the third clock. Okay, so this also explains the second doubt that most of you have, which is this. Because when my y changes over here, okay, basically once my output becomes 1, my y can change anytime. Okay, between this clock and the next clock here. So any point of time it can change. So you could have changed here, okay, or you could have changed a bit later, doesn't matter. Okay, doesn't matter. Okay, because I still have to wait for this clock. I still have to wait for this clock before I can register a change. So when this clock comes in, again I sample the value of y. Okay, so when the clock comes in, I sample the value of y. If y is 0, then the output z will transition to a 0 here. Okay, if y was still 1, then the z would have remained as 1. Okay, so I think most of you have some doubts because you are still not understanding or still have some issues about the impact of the clock. You have to remember, in sequential circuit design, we sample the input and process it only at the clock edge. So in between two clock edges, even if there are changes to the signal, doesn't matter. Your signal is not going to be affected. Your circuit output is not going to be affected. Okay, we only process the input, okay, at the clock edge trigger. Okay, so always remember this. So that is why, okay, that is why over here, okay, for this doubt over here, even though my input changes, I have to wait for the clock. Okay, so at this point of time, I'm still in state 2. Okay, so I have to wait for the clock before I go to a new state or change the output. Same thing over here in state 3. Okay, the input can change while I'm in state 3, but when I'm in state 3, okay, the output is supposed to be a 1. Okay, then this new input will be processed only at the clock edge trigger, and then I will decide what is the next state to go through. Okay, so the output of the circuit is generated based on that particular state's values. Okay, and then the input is factored in to determine the next state that I go to. Okay, so I hope this sort of clears up the doubt that quite a few of you were having, okay, regarding how we actually can come up with this table. Okay, again, many of you have different solutions in terms of the way you think, or cutting down from 4 states to 3 states. Okay, I may not be able to go through all your solutions that you're emailing me, okay, but as long as you understand the thought process, okay, and understand the impact of the clock, then I think you are good. Okay, so do not be overly concerned. Okay, so I hope this clears up any doubts that you are having about the practice question that I sent. Okay, thank you.